Welcome everybody to our ACM Distinguished Colloquium event today. We are very pleased to have Dr. Zhuge from Aston University in Birmingham, UK. He's been there for 2 years now, but he also holds a joint appointment in China, Chinese Academy of Sciences, and is an expert on semantics applied to computing anywhere. You see, so it's a very, very important topic, and he's going to give us a lecture. I have a slightly different title here, so maybe we go with that title, okay? Or we can read both the titles. From Big Data to Knowledge with Cognitive Cyber Infrastructure is the title I have there, but we have
it's too long.
Too long. Okay, you shortened it. That's right. Okay. So mapping big data into knowledge spaces.
Okay. Yes. Okay. Thank you very much, Raj, for the introduction. And I would like to take this opportunity to thank ACM who makes this lecture possible. This is a part of the lecture of ACM Distinguished Speaker Program. First of all, I would like to introduce the background of big data. So we have experience of using Google. Google has already processed big data, 24 petabytes every day. And we use translation, Google Map, and also Google Flows. It's also big data. Actually, the Google Flows, people calculate, the propagation of the people search the flu and real flu propagation. The results say reveals that the two flows very close. So this is and also big data reflects the a kind of reality and human desire. Because the reality is that data is spent on the social network, internet with mobile phones, and many inventions of devices. And because the big data, people is getting harder, it's feeling harder and harder to process the big data. We don't have a good model, we don't have good tools and methods to process the big data. On the other hand, human want a process, a method to process big data, because we lack the appropriate model to process big data. So there's a reality, it's a fact, big data expanding, and a lot of new devices connect to the internet, and we lack of a model, a good model. Actually, there's no one model to dealing with all the aspects of big data. So we need, we hope big data can help us. And capability. What is the capability of big data? Can big data dealing with all the things, help us solve all the problems? So this is about big data. So that's why big data attracts so many eyes, so many interests of not just the research community, but also the industry and the governments. So the current understanding of big data is about 4 V's. For example, Gartner, according to Gartner's understanding, is big data is about volume, big volume of data, and the variety of data, structured and unstructured data, and the velocity. The data change, stream data change frequently, and the value. It's about not just about big data, it's about the value on the data. The data is relevant to the business. And IBM has its own understandings. It's mainly focused on the raised performance of the enterprise information systems by adding some conditions. And some research propose data science as a science. The problem is if you call big data as a science, we need to ask what is the fundamental principles? What is the laws, basic laws of the science? And data itself actually is a consistent research issue in the development of computing. In early stage, we structured data in program, and then we separated data from program, just like database. And then we distribute data And the World Wide Web actually is distributed data. And it's loosely related to search engine. Search engine, program of search, the designer of search engine is separate from the web page designer. So it's separate. And in object-oriented, data is encapsulated in objects. So data is the research issues in the whole development history of computing. So this is data, history data. It's not at the current stage, all the computing history. And we also need to mention the big networks, the social networks, World Wide Web. World Wide Web itself is big data. And it's also, these networks also generated data. So we need to concern not just data, we need to concern the system that generates data. And also, big data search needs the fourth industry revolution. No, the first industry revolution, second generation industry revolution. Now the fourth generation, the fourth industry revolution is actually is intelligent manufacturing. It's the invention of the multidisciplinary innovation of industry, manufacturing. And on the other hand, the revolution of internet. The two revolutions converged to generate the fourth industrial revolution. So big data, one of the background is the fourth industrial revolution. So this is big data search. This is just an example from the Rolls-Royce big data. Variety, how to, it's about design the products. Design, for example, design the wheels. Wheel is not the data. It's about not just the physical data. It's about service, the styles, features, functions, impacts. So it's about all the aspects of the product, one product. A lot of information, a lot of data. How to integrate the data, provide the designer on-demand service. So this is a kind of collect and summarize all information about one product. The data is concerned with videos, pictures, documents, data. So, variety. This is an example. So this talk is about, there are several keywords of this talk. Big data. Big data is about, we need to concern what is the basic methods of dealing with big data. A lot of methods, data mining, statistics. What is basic methods? What is the capacity of big data? And what is the limitation of big data? The second keyword is science paradigms. Big data is not just data, it's about the science paradigms. So when science paradigm is generally stable, when the new paradigm, most researchers follow the single paradigm. But when big invention, just like Einstein theory proposed, then the new theory reduced old theory into a special case. For example, Newton's laws. It's a special case of the physical laws. So it's about the science paradigm. So some researchers have proposed, now we are entered into a model-driven science paradigm, into a data-driven science paradigm. So science, big data is not just data providing you information. It's about the research paradigms. Then the knowledge. So human understand facts, represent the real world, and human can transform the reputation into knowledge space, but machine cannot. So this is the big difference between machine and human. problem is, can we generate, can we transform big data into knowledge? It's a challenge. So, and then, what is the nature of big data? Big data is four V, volume, variety, volume. But what is the nature? What is the nature of big data computing? What is the difference between big data computing and the traditional computing? And the next keyword is cyber infrastructure. How to invent a new cyber infrastructure to support the big data computing. What is the fundamental challenge of big data computing? So these are keywords. Now, let me tell you implicit web of dreams in the history of computing. The first dream should be Babbage dreams. He proposed 200 years ago. He proposed the automatic computing engine. That's mechanical, not electricity. And half century later, mathematician Hilbert, he proposed a dream. He wanted to establish mathematics on a solid and provable consistent foundation of actions. All mathematical truth could be deduced. His dream. And he proposed a problem. Could an effective procedure be devised to demonstrate in a finite time whether any given mathematical proposition is or is not provable from a given set of actions? This is a so-called decision problem. And he also proposed 23 hard problems. This problem becomes the lifetime, endeavors for almost all mathematicians at that age. Some problems have solved, some problems still have not solved. Turing solved one problem. He invented a Turing machine to answer this problem. He solved the problem. It's very different from mathematical solutions. He invented the Turing machine that simulated the human problem-solving process. Because human solve problem needs a pen, needs a paper. Your answer should write on your paper. His machine just simulated very basic steps of the human problem-solving process. So this is Turing. He also proposed his dream. His dream is an intelligent machine. And proposed a Turing test. He published this idea in 1950, and actually, artificial intelligence area extend his dream. And in America, von Neumann extended Turing machine, realized Turing machine. He built the first computer in Princeton Advanced Institute in the basement. One of the most important ideas is aid memory, because Turing machine there's no memory, aid memory, and regarded as a program, because at that time memory is very expensive. If you store data and a program in the same storage, then storage then will be cheap. So this is one of the good idea. And he also proposed his dreams. And actually, the development of a computer is towards the faster and smaller. His dream is self-replicating machine. So, von Neumann actually realized he made the Turing machine and realized the Babbage dreams. Babbage dream is mechanical, it's electrical in a computer. So in America, there's a big man called Bush. He proposed his dream in 1945. The next, actually, it is a vision of internet and multimedia. The next can contain all human knowledge, his dream, and contain billions of books, hyperlinked. So he actually foreseen the World Wide Web. And record everything you can see, a machine with types, and then talk to, and navigate by text search, follow links association. So it's a World Wide Web. So his dream is actually information storage and access. But at that time, there's no computer. So this is the dream. This dream is generally realized. And Tim Berners-Lee realized his dream. He proposed his dream. His dream is a powerful means for collaboration between people and machine. It's not just the internet. The World Wide Web is not just the connection of machine. It connects people. And Jim Gray's dream. Jim's great dream actually extended the Bush dream. He proposed the personal memex. The personal memex can remember what is seen and here, and quickly return any items on request. It's just like some intelligent multimedia. And the word memex, it can record everything. So actually, it's big data. And answer questions, and summarization as experts, giving you 1,000 paper. Can you summarize, automatically generate a survey paper? And quick, precise, and quickly. So this is a development of dreams in computing history. So big data actually is not new. Big data is actually is from Bush, and computing, it's a computing history. So the big data was boom in about 6 or 7 years ago, when Jim Gray talked at a meeting in the United States. He proposed data-intensive scientific exploration. So that's the milestone of big data. And his colleague, published a book called The Fourth Paradigm of Data-Intensive Science Discovery. So big data is not just data management, data processing, data mining. It's about scientific research, scientific methodology. So initially, scientific research is an experience based, and then developed to theory. For example, Einstein in computing is computer theory, theoretical computer science. Computation is the development of a computer, and simulation. And now we are entering into a data exploration age. We need new tools and methods. It can integrate all these methods. So this is about the science paradigms and the data. So when we talk about data, we need to see the observed systems. For example, the universe. We need to concern the system that generates data. We observe the systems and generated data and analyze data. We generate knowledge, use our mind. This is a problem. Traditionally, we use our mind. But some people, some researchers, just exploring data. They don't need to observe the system directly. Now the problem is that we need to use computer to help us to explore the data and help us generate knowledge. So how? And with the development of, with the evolution of the observed system, data expanded and knowledge expanded. How to predict the changing order. So this is a problem. So we need to conserve not just data, we need to conserve the observed systems and the knowledge. How to map the data into knowledge. So apparently there's no direct mapping. Traditionally we use our mind to map data into knowledge. So how to use computers to map data into knowledge. With this knowledge we can predict changing world. So let me describe an example of basic methods of linking the data. Data is not just data, it's about the network, the systems that generate data. So for example, we write papers. We are the author of a paper. We publish it in a journal. And some people read the papers. And it's the reader of. We have co-authors. The reader write their papers and publish in other journals, and decide the new paper, cite the old paper. So these networks evolve continuously. So it's a changing network. The nodes and the links are not just data. It's active, it's person. It's semantically rich links. There are some implicit links in the network. So the network evolves. So for example, after I publish a paper, I usually revise about my homepage. And some people read my homepage and send me an email and invite me to a conference, give a talk. So this is an evolution of the network. So the problem is, this is just a simple example. It can be lifetime, when you do research, your network expands in your lifetime. So this is a big network. So the problem is so these are features of the network. For example, it's open. There's some complexity on the network. And the influence of 8 nodes or remove nodes or 8 links, remove links, the influence sometimes are local and sometimes are global. And the problem is how to model this kind of big network. And what is the rules, the motion principles, and how to discover the implicit relations, and what is networking effect? What is the emerging semantics? For example, the evolution of network can emerge some communities, and each community represents some semantics. So what is the semantics? And what is the interactive semantics? Because the people involved in the network interact with each other, and they can understand some, they generate knowledge. What is the interaction? The semantics is not static. It involves with the interactions. So what is reachability in the network? And what is the principal method for dynamic knowledge sharing? So these are network systems. It generates data, itself is a data. How to analyze the big data? It's actually how to analyze the big network. Complex semantic rich network. Another form of big data is for example, a city. We can observe the city from different dimensions. If we increase the dimensions, the volume of data can be significantly reduced. For example, the city, there are some data about the law, some data about transportation, some data is about education, some about environment, some about economy, even economic, huge amount of data. So if we can separate it, set up appropriate dimensions, user can be only interested in focus on several dimensions. For example, this user only interested in economics at certain time, and also because the economy relevant to the environment, and also relevant to transportation. So this user can only access the 3 dimensions. So data analysis is actually how to select the small number of independent dimensions among large-scale dimensions. The actual dimensions represent the human minds, human understandings of the big data generated in the city. And different people have different understandings. But when people interact with each other, community will form. And the people and dimension in the one community, they have consensus on the dimensions. So this is about the analysis, big data analysis, dimension and big data analysis. Okay. And we observe, this is the observed system generated data, and the user is also systems. User also generated user data. So when it is actually a dual system, when we observe the systems, we should not forget the user. And we need to observe the system user and observe the system generated the data generated by the system and also the user data, and put the data and systems into a multidimensional space and carry out the data analysis. So this is about data analysis, not just analyze data. We observe the system, user, and multidimensional. The dimension can be time, operation, value, behavior. This is an example of using big data model in enterprise strategic planning. This is a physical space. Physical space generates data, big data, for example, energy, material, environment. Because a company, a factory produce need energy, material, and also it's a part of society. Society generates some information, for example, competitors, customers' information, and the data about the market, policy, etc. And the production process also generated data. For example, purchasing, organizing, deliver, sales, research and design, also generate a lot of data. So these different aspects of different dimensions of data will be integrated and form dimensions and links, and construct a data space. This kind of data can be multi-dimensional. And different dimensions of data provided different models. For example, supply chain analysis needs some dimensions of big data. And life cycle analysis needs different dimensions of data. Competition analysis needs different aspects of data. So these models coordinate and provided strategic planning. So this is an example of strategic planning in industry. Now we are talking about knowledge. When Bush, when he proposed the next idea, actually he said, with many science and technology have extended our physical power, and but seldom extended the power of mind. So access to a command over age, knowledge of ages, is a great challenge. So at that time, he proposed the idea of how to extend the power of mind. So we can see computer is about representation. Data in computer is represented in certain forms, data structure, and for example, HTML, XML are all representations. Different representations can be transformed. So one idea is whether we can transform data in one form to another form, whether we can realize transformation from data into knowledge. So this is a very difficult because the meaning of reputation is very difficult to determine, and the expression ability of reputation is difficult to determine, and the mapping of the meaning of a mapping is difficult to determine, and the correctness of mapping, the correctness of this mapping from this reputation to another reputation is difficult to prove. And the completeness of reputation is difficult. For example, there are a lot of reputations, HTML, XML. How can you guarantee this kind of reputation is complete? So these are difficult. So many artificial intelligence systems fail. No, and knowledge-based systems fail because these systems do not, distinguish data, information, and knowledge. They try to represent knowledge, but actually, in data, it's kind of data representation. So, for example, they invented the production rules, try to represent human knowledge, experts' knowledge. A lot of expert systems developed, but finally failed.
What do you think about Psych and SCOAN?
Oh, Psych.
Have you heard of those?
Yes, it's not it's different from Actually, I think it's a kind of a reputation, simple reputation, knowledge reputation. Yeah. It's not successful.
But what
From my point of view, it's not successful.
So there,
and especially in the internet age. Now, it's kind of it's an age of community participation. You cannot rely on several people to develop human knowledge.
wait, couldn't you have like a Wikipedia-like thing? Where, like,
Yeah,
you have, like,
Wikipedia is the
multiple-
right way.
No, I mean like something like Wikipedia, except it's like sort of like Psych, where you sort of are showing relationships and people come in and edit it and argue about what types of relationships.
Yes. Some people think in this way. Yeah. There's a special issue in artificial intelligence journal that's talking about how to extract some so-called knowledge from Wikipedia. There's some work that has been done. Yeah. Actually, my next stop is Los Angeles. There's a company who want to talk to me to extend Wikipedia to the next version, make it more intelligent, make it more semantics.
Isn't there already a semantic Wikipedia called like I think DBpedia or something like that?
Yes.
And so what are the problems of that? Why do you think?
Oh,
that
so there's a secret. Okay, because it's a business secret. So
okay.
let me finish this first. Maybe we can discuss later. Okay. So this is a kind of this part is evolving cognitive systems. So people interact with each other. So we need to think about this part. This is user. This, for example, is a computer, cyber systems. Human interact with the cyberspace. We provide assume. We provide design. We observed. We read the reputations. We can evaluate our assumptions. But actually, we interact with each other. Knowledge exchange between humans. And in human, we have a personal knowledge space. And the internal, we have the internal reputation in mind. And people interact with each other to increase our knowledge. And also humans interact with the cyberspace. We represent, read. So this is a kind of interactive system, closed loops. So we should not forget this part. And also there's a virtual knowledge space. There are some theories, methods, principles, rules. For example, physical laws, natural laws. This is a virtual knowledge space. So this is a kind of interactive mapping from the observed systems to knowledge, from data to reputation, and through the so-called evolving cognitive systems. This is a community. And then generate some knowledge. So we should build some ecosystems consists of cyberspace and cognitive systems. One important basic idea, unit of knowledge is concepts. So we have a lot of text on the web. We many systems analyze the text, how to extract knowledge from text. Text actually is data. It's a kind of data, structured data, and unstructured data. But there are some language use knowledge and knowledge about language reputation and knowledge about the physical, for example, the knowledge to be represented